Today's lesson will serve as an introduction to our electrochemistry unit. Electrochemistry is the study of how electrons are transferred from one chemical species to another. Throughout this unit, we will be studying reduction-oxidation reactions, or redox reactions for short. These are a special kind of reactions that involve the transfer of electrons between chemical entities. In these reactions, one entity will be reduced and one entity will be oxidized. Reduction is the process in which an entity gains electrons. Oxidation is the process in which an entity loses electrons. We say Leo the lion says grr to help us remember which is which. Leo stands for losing electrons is oxidation, and grr stands for gaining electrons is reduction. Here is a general diagram which shows how electrons are transferred between entities in a reduction-oxidation reaction. There are a lot of different types of redox reactions. As long as electrons are transferred, the reaction is considered a redox reaction. Double replacement reactions do not involve an exchange of electrons, so they are not classified as redox reactions. The remainder of this lesson focuses on oxidation numbers. Oxidation numbers are a system that chemists created to explain observable results. It will be very important that you understand how to assign oxidation numbers because we will be working with these throughout the electrochemistry unit. There is a system of rules that you will be expected to remember. The first rule tells us that elemental atoms have an oxidation number of 0. This means that any element will have an oxidation number of 0. This rule holds true for diatomic and polyatomic molecules. If we have an ion with a charge, the oxidation number for the ion will be equal to the charge of the ion. Iron 2+ has an oxidation number of 2+. Sulfur 2- has an oxidation number of 2-. Fluorine is a special element because it will always be assigned an oxidation number of -1. Oxygen almost always has an oxidation number of -2. If oxygen is in a peroxide compound, then the oxidation number for oxygen is -1. This explains why the oxidation number for oxygen in sulfur dioxide is -2, but the oxidation number for oxygen in hydrogen peroxide is -1. Hydrogen is also assigned a specific value for oxidation numbers, depending on what it is bonded to. In most cases, the oxidation number for hydrogen is +1, but when it is bonded to a metal, it has an oxidation number of -1. Rule 6 explains how we can solve for the oxidation numbers of atoms that don't have specific rules. The total of all the oxidation numbers of all the atoms in a molecule is 0. For N2O5, we will enter in the values that we know. We know from the rules that the oxidation number of oxygen will be -2, and the total of all the oxidation numbers will be 0. This means that we can solve for the unknown value of the oxidation number of nitrogen. A similar procedure is used to determine the oxidation number of phosphorus in the second example here. Halogens will typically, but not always, have an oxidation number of -1. You can only have one unknown, so if you need to find the oxidation of the other element, use -1 for halogens. If you have a complex ion, the total of all the oxidation numbers of the atoms will equal the charge of the complex ion. Review each of these examples to see how the oxidation numbers are calculated. To summarize, there is a systematic way to assign oxidation numbers for atoms. Start by assigning the oxidation numbers that we have rules for. Then we set the molecule or ion's oxidation numbers equal to the net electric charge for that molecule or ion. Then we should be able to solve for the unknown value. Oxidation numbers that are fractions do exist. Please complete the October 2nd quiz.